A sine B times the quantity x minus h plus k, or y equals A cosine B times the quantity x minus h plus k. What I'm going to have you do is step 1. We're going to graph y equals A sine bx or y equals A cosine bx. Then step 2, you're going to shift the graph h, comma, k. So before we do this first, I want to take you back to quadratic equations and the graphs. If you remember, this was our general form. Y equals A times the quantity x minus h squared plus k. So if I gave you y equals 2 times the quantity x minus 1 squared plus 3, how does this graph shift? Just looking at the equation, how does this graph shift from the parent function? Anybody want to try it? Jonathan?
Right 1 up 3.
Good job. This one shifts right 1 up 3. And do you remember the silly little sentence we came up with, or actually one of my other classes did? It was vacuum often in socks only. Vacuum often in socks only means the vertex is the opposite of the inside, the same as the outside. So it's the opposite of minus 1, so it's right 1, and it's the same as the outside, it's up 3. Okay, so having reviewed that, let's look at this example. It says, how does the graph shift from the parent function y equals sine x if I have y equals sine the quantity x minus pi over 2 plus 3? Okay, who wants to try this one? Alex?
Right pi over 2 and then up 3.
Good job, you got it. Okay, right pi over 2, up 3. So what's really nice is in Algebra 2, we've studied absolute value equations, quadratic equations, square roots, cube roots, rational functions, logarithmic functions, exponential functions. They've all used that vacuum often in socks only, and that does apply to our trigonometric functions as well. All right, so here we go. In example 1, if I'm going to start shifting left, right, or up and down, the first thing you're going to do is you want to graph y equals A cosine bx. Then step 2 is you're going to shift h or k. Sometimes it's both, sometimes it's just one of those. So here's what we're going to do. So I'm going to start with graphing y equals, in this case, it's cosine x. So we identify the amplitude is 1. The period length is 2 pi because it's 2 pi over b. So we're actually now doing y equals cosine x based on the previous lesson. And we spent 2 days on that, so we should be in pretty good shape now. I'm going to make 4 tick marks to the right, label it the period length. And I'll go up and down the amplitude, so I go up 1 and down 1. And I have to tell you, I used to make students do 2 different colors with these, and I'd had a student who went to a different school said, oh, my teacher has us make a dashed one and then a solid one. And it was one of those, duh, that would be way easier than trying to do colored pencils. So I'm going to use the dashed and the solid. Dashed will be this first graph, solid will be the ending graph. So cosine starts at the amplitude. And watch what I mean by the dash. This is not the final graph. And some of you, when you pick up on this, you'll be able to do 1 graph. You will not need to do 2. And that is absolutely fine. But let's do the first few this way. And then if you can visualize the final graph without drawing 2, you are more than welcome to do that. Okay, now looking back at the original equation, how does y equals cosine x plus 4, how does that one shift? Up 4. So now, watch what I need to do. I'm going to go back to my grid, and 1, 2, 3, 4, I need to go up 4 units. So you want to use, that's why we use pencils. So you can erase your arrow and move up the y-axis 4 places, and then watch what you're going to do. You are just taking this graph and you're going to shift every single point up 4 units. And then once you do see the pattern, you can just follow the pattern. And then what's really neat, when you do the dashed graph, you can actually see the dashed graph has been shifted up 4 units. Okay, very nice. All right, let's look at example 2. It says y equals sine the quantity x plus pi over 2. So the first thing we're going to start with is y equals sine x. So I identify the amplitude and period. The amplitude is 1, and the period is just 2 pi. So I make 4 tick marks to the right and label it the period length. And then I'm going to graph y equals sine x. So you always start with y equals a sine bx or y equals a cosine bx. Okay, you don't put the h and the k part in. So sine starts at 0. The amplitude's 1, so we now know how to make that graph based on what we did the last 2 days. And I make that dashed. Now how does this graph shift?
Left pi over 2.
Good job. That's left pi over 2. Now on these first several, my period length is 2 pi, so it's not really adjusting. But what you do need to be very, very careful with is you have to determine what is the length of a tick mark. It's not always the same on every graph. It varies depending on the period length. So in this case, 1 tick mark is pi over 2. So I'm going to need to take every single point and move it left 1 tick mark, because that's left pi over 2. So I do need to add 1 more tick mark here, and then this one will be solid. And then it's really neat to look at. You can see the graph has been shifted left pi over 2. Any questions on the first 2 examples? All right, then let's move on to example 3. We're going to start with y equals 3 sine x. So my amplitude is 3. The period length, remember, period length is found by 2 pi divided by b. If there's no number in front of x, b is understood to be a 1. So that's 2 pi. So I make 4 tick marks to the right and label it 2 pi. My amplitude is 3, so I'm going to go up 3 and down 3. Now the sine curve starts at 0. So I go 0, up to amplitude, down to 0, down negative 3. This one, remember, is the dashed graph. And then how does y equals 3 sine the quantity x minus pi over 2? How does that one shift?
Right, pi over 2.
Right, pi over 2. So again, it's important to know what a tick mark represents. On this graph, one tick mark is still pi over 2. So I'm going to need to add one tick mark to the right, and you're going to move every point to the right one tick mark. And then this one will be your final graph, and it's solid. So again, let me restate that. Dashed graphs are your initial graph. Solid graphs are the final graph. So when I'm grading this on the next quiz, I'm going to be looking at your solid graph as your final answer. Okay, let's go ahead and take out the graphing calculators a moment before we do example 4. I want to do a small exploration here. And I'd like you to go to your Y screen, clear out anything you have in there, and I want you to put sine x, and then I want you to put negative 3 sine x. Let me say that again. Take out your graphing calculators. In y sub 1, I want you to put sine x, y sub 2, negative 3 sine x. Now we played around with the window, so let's go back to Zoom and do Zoom 7. Zoom 7 is the trig window. So here comes my parent function, and then here comes the negative 3 sine x. What I want you to notice here is that obviously the amplitude was your 3 and your negative 3. However, instead of it going up to 3 when you have a negative out front, it reflects it over the x-axis, so it actually goes down first. With cosine, if there's a negative out front, if a is negative, instead of going up to amplitude, you go down to amplitude. Okay? So let's go back to our notes. So when I do this one, remember how in 14.1 I kept telling you, I know it seems silly that I'm putting the absolute values around a, because they were all positive, and I said it's because what's coming, a can be negative. So amplitude, the definition of amplitude is 1/2 the distance between the maximum and the minimum. Distance is non-negative, so it doesn't make sense to say amplitude's negative 2. The period length is still 2 pi. So this one's going to have only one graph. Do you notice I don't have an h or a k? So I only have one graph. So the only time you're going to do dashed and solid is if you have h or k or both. So here we go. Instead of this starting up at positive 2, this is going to start down at negative 2. And again, it's solid because I don't have any other shifts going on. Another thing I want to point out to you is when you're graphing sine and cosine, I want you to notice that where you start and where you stop should be the exact same y value. So I'm down here at negative 2, it ends at y is negative 2. Okay? So when a is negative, it's a reflection over the x-axis. Okay? All right, everybody have it? All right, let's look at example 5 then. Example 5 says graph y equals negative 3 sine x plus 2. So you want to start with y equals negative 3 sine x. So the amplitude is the absolute value of negative 3, and the period length is still 2 pi. I know that's not very interesting. We haven't changed the period length. Okay, again, y equals negative 3 sine x. The period length is 2 pi, so we make 4 tick marks to the right, label it the period length. The amplitude is 3, so I go up 3, down 3. Now the sine curve starts at 0. So I start at 0, but because a is negative, instead of going up 3, I go down 3. And then I just follow the pattern. Oops. Oops, sorry. This is supposed to be dashed. Caught it? Okay, so this one's dashed. I'll continue the pattern going to the left. And then how does this graph shift?
Up to.
Up 2. It's actually going to go up 2. So that means I need to go back to my y-axis and move that up to 5 because it's going to go up 2 units. So all this means is I take every single point and shift it up 2 units. And again, if you see a pattern with this, and you don't have to literally count up 2, then you are welcome to use the pattern. Okay? All right, any questions on that one? Okay, then let's do example 6. We're going to start with y equals 2 sine 4x. Remember, you start with y equals a sine bx. The only thing you don't include is an h or a k shift. So this one, we actually get a different period length. The amplitude is 2, but my period is 2 pi divided by 4, or pi over 2. Okay, so finally, something different. So I'm going to make 4 tick marks to the right, and it's pi over 2. What is the second tick mark, Alex?
Pi over 4.
Pi over 4. My amplitude is 2. And I'm going to go ahead and do this first one in a dashed graph. So sine starts at 0. It's positive 2, so I go up to 2, 0. Then my graph is just shifted up 3 units. So I'm going to take every single point and shift it up 3 units. Okay, does this seem as straightforward as I think it is? Okay, so again, you start with y equals a sine bx, or y equals a cosine bx. Draw it in a dashed curve, and then you do your h and your k. All right, I'm going to give you a head start on me, and I want you to try example 7 on your own. And if you're a fast worker, go on to example 8 if we're still waiting. Okay, if you're struggling to get started on this one, you're going to start with y equals negative sine 1/4 x. The amplitude is positive 1. The period is 2 pi divided by 1/4, which becomes 8 pi. So you make 4 tick marks to the right, label it 8 pi. The amplitude's 1, so I make an up 1, down 1. Because there's a negative out front, a is negative 1, I'm going to start at 0 for sine and then go down 1. Then my shift is down 1 unit. So I'm going to just go through and every single point I have plotted, I'm going to move it down 1. Okay, so there's my final graph. Any questions on example 7? All right, then try example 8. I'll give you a head start. So I'm going to start with y equals 5 cosine 2x. So the period length is 2 pi over 2, and the amplitude is 5. So I go 4 tick marks and call it pi. So halfway is pi over 2. So now what's interesting about this one is the shift. So cosine is going to start at 5, go down to 0, negative 5, 0, back to 5. This one's dashed. Now what kind of shift do we have here?
Down pi.
Nope, not down pi. You're actually going to go to the right pi. Now, what I mentioned earlier is that you have to be careful when you're doing that left-right shift. You need to know what 1 tick mark represents because 1 tick mark is not always pi over 2. In this case, how many tick marks is equal to pi? 4. 4 tick marks is pi. Because look, we went 4 tick marks and we went out to pi. So I'm actually going to need to add 4 tick marks and call that 2 pi. And then I'm going to take every single point and move it right 4 tick marks. But something very, very interesting happens here. Yeah, do you notice it starts overlapping? It is. Good notice there, Seth. It actually, if I continued it, it overlaps the entire way. Why does it overlap? It's really the same graph. Because this one didn't stop here, it kept going. And so when I shifted, if I kept going, it really is the exact same graph. Why is this shift the exact same graph back onto itself? Alex?
Is it because we moved over pi and that's what our period was?
It is, exactly. If you shift the period length, you're just taking it right back onto itself, okay? Good conclusion. All right, I'm running low on time, so we're not going to get to example 9. And in example 10, you're going to have some in the homework where I don't know why our textbook chose to change it like this. But I want to point out when you do problems like this, just use the commutative property and switch the order. That's all you're going to do is switch the order.